Welcome back. Let's talk some more about orthonormal bases. Shall we? So let me remind you what an orthonormal basis is. You have a vector space V and an inner product and a basis. You say that the basis is orthonormal if the VI's are orthogonal, if I is not equal to J, and the length of VI, each VI, is equal to 1. And, of course, the standard example is Rn with the usual dot product, and you let VI be 1 in the ith place. So last time I talked about just some sort of generalities about orthonormal bases and gave some idea about constructing them. And that's kind of a warm-up for today, which is to answer the following question. How do you construct an orthonormal basis? And in particular, can you always construct an orthonormal basis? And I'm going to give a refinement of this, which is called the Gram-Schmidt process. The Gram-Schmidt process, or sometimes called algorithm, is a method for constructing an orthonormal basis, and it always works. So it's So the answer, or an answer to this question, is provided by our famous thing called the Gram-Schmidt process. And this is an algorithm for constructing an orthonormal basis. And in fact, what it does is, starting with any basis, it constructs a new orthonormal basis out of it. Well, that's a little vague. What do I mean? How are these W's related to the V's? I'll explain that. But the Gram-Schmidt process is a process which the input is any basis and the output is an orthonormal basis. Let's illustrate this with a very simple example from R2. So we have R2 with usual dot product and an arbitrary basis W1, W2. And what we want to do is we want to take the basis W1, W2, and from that I'm going to construct an orthogonal basis V1, V2. And that's good enough because we know how to go from an orthogonal basis to an orthonormal basis. We talked about that last time, and I'll call the orthonormal basis now U1, U2. But this is the main step, getting an orthogonal basis. So how do we do that? Well, we start with W1 and W2, and we want to get V1 and V2. So what would you like to take for V1? Well, let's just take V1 equals W1. So that is to say, we just take this to be V1. That's a perfectly good start for an orthonormal basis, or an orthogonal basis. And now what do you want to take for V2? Excuse me. What do you want to take for V2? Well, here's the idea. We already have W1, and so we know what direction V2 is supposed to be in. You have to take the line perpendicular to W1, and the vector v2 is supposed to be along this line, so it's perpendicular. And a natural thing to do is to take the projection of w2. So that is to take this to be the vector v2. And that's basically the Gram-Schmidt process. This is V1, and this is V2, and that's our new orthonormal basis. So what is V2? V2 is equal to W2, and then you're subtracting this blue vector. And what is this vector? Well, it's in the direction of W1, in the opposite direction. So it's some scalar times W1. So what we're going to do is we're going to take V2 to be W2 plus CW1. Right, that's this triangle here. V2 is W2 plus CW1. And we're going to choose C appropriately. So let's look at this a little bit more closely. Here's the same picture pared down a little bit. There's my two vectors W1 and W2, and I set V1 to be W1 and V2 to be this guy. And as I said before, I want to know what C is equal to. And in order to do that, how do I know what C is supposed to be equal to? Well, I need to choose C so that V1 and V2 are orthogonal. So I want to make V1, V2 equal to 0. And, well, what is this? Well, V1 is W1, and V2 is W2 plus CW1, which I can write out as W1, W2 plus CW1, W1, and I'm asking you to pick C to make this 0. And it's always good when you have an equation like this to pause and think, is this reasonable? Well, let's see. I know W1 and W2, so I know this number, and I know this number, and therefore I know this number. I simply take C is equal to minus W1, W2 over W1, W1. Okay, so the first step of the Gram-Schmidt algorithm, I'll write it over here, is you take V1 is W1 and you take V2 is W2 minus, I'm going to rewrite it slightly now, W2 V1 over V1 V1. That's the main formula. Okay, so I rewrote this slightly. I just replaced W1 here with V1 in 3 places, and I also switched the order in the numerator. That's not important. So this is the formula for V2. And so now if I wanted an orthonormal basis, I would simply take the same thing and take U1 is V1 over the length of V1, and U2 is V2 over the length of V2. This will be orthonormal. This here, of course, is just orthogonal. Okay, so let's state the general Gram-Schmidt process. So we're given a vector space V, an inner product, and an arbitrary basis. And we're going to construct an orthogonal basis, V1 through Vn, orthogonal. And the way we do that is we take V1 to be W1, And we take V2 to be the formula from the previous slide. V2 is W2 minus W2 V1 over the length of V1 squared times V1. I wrote the denominator in a slightly different form. And now what are we going to take for V3? Well, I want to take W3, and then I want to modify it by some multiple of V1 and some multiple of V2. And I want to choose that multiple so that V1, V3, and V2, V3 are both 0. And the way I do that is I choose the multiple as follows. Here I put W3 V1 over the length of V1 squared, and here I put W3 V2 over the length of V2 squared. So I suggest that you pause the video here and you check that that with this choice that these conditions hold. That this vector V3 is perpendicular to V1 and perpendicular to V2. All right, good. I'm glad you checked that. Let's write down the general formula. So VK is WK plus, well, it's going to be some linear combination of the preceding V's. And the preceding example, or the preceding cases, suggests what a formula for CJ should be. It turns out that CJ is minus WK VJ over the length of VJ squared times Vj, where J runs from 1 to K minus 1. So this, in some sense, is the heart of the Gram-Schmidt process. Let's just stare at it for a minute. It's an inductive procedure. You compute these vectors one at a time, V1, V2, V3. And once you've computed the first K minus 1 of them, you can compute the next one by taking WK plus this linear combination of the previous ones, where the constants are given by this formula, which involves the VJs that you've already computed. Okay, so I'll do an example in class, of course, and let me just summarize it in another restatement. This can also be stated as follows. The Gram-Schmidt process says that VK is equal to WK minus the summation, J runs from 1 up to K minus 1, of WK VJ over the length of VJ squared times VJ. So this is just really the same thing as this. It's just put in summation notation. And maybe this is a good place to say that if you come from a red state, you could use this formula, and if you come from a blue state, you could use this formula. Sorry, that's an election night joke. Okay, so what did we just do? We were given vectors W1 through Wn, a basis, and out of that we computed an orthogonal basis, V1 through Vn. And let me remind you that you could also have gone on to compute an actual orthonormal basis, U1, Un. The normal part just requires taking Ui to be the normalized vector Vi. And, well, as I said, I'll do an example of this in class. What I want to do next is a variant of this. And the variant is, rather than computing the v's and then normalizing at the end, the variant is we normalize along the way. So we set v1 is equal to w1, and then u1 is equal to v1 over the length of v1. We do that right at the beginning. And then we're going to work with, instead of the v's, we're going to work with the u's at each step. So the next step is you write v2 is equal to w2 plus some constant, not times v1, but times u1. Okay, and I'll come back to the constant a little bit later, but in any event, you do that, you figure out the constant, and you then normalize and say u2 is equal to v2 over the norm of v2, and you keep going. So at the kth step, you're going to write vk is wk plus c1u1 plus dot 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 ck minus 1 uk minus 1. And assuming that you can figure out the CIs, you can then set UK is equal to VK over the length of VK, and so on. So it's a very similar process, and clearly these constants are going to come out a little bit differently. And it turns out that the constants work as follows. So what have we done? We had a basis W1 through Wn, and out of that we constructed an orthogonal basis, V1 through Vn. And let me remind you that it's easy to go further and construct an orthonormal basis, U1 through Un. You just have to normalize. You take the Ui's or the Vi's divided by their lengths, the normalized Vi's. And as I said, I will do an example of this in class. What I want to do now is a variant. So what we did here is we constructed all of the v's, and then at the very end we normalized them to get the u's. In this variant, what we're going to do is normalize along the way. And I'm going to write this algorithm in a slightly different form. So the first step before was to write W1 and then take V1 to be W1, and then take U1 to be V1 over its length. That's clearly the first step in order to get U1. But I want to turn this around slightly, and instead I want to write W1 is equal to some constant times U1. Well, V1 is, according to this, W1 is the length of W1 times U1. So R11 is simply the length of W1. And then I want to write W2 is equal to R12 U1 plus R22 U2. I want to pick two unit vectors, U1 and U2. I want U1 and U2 to be orthonormal in such a way that this new vector W2 is a linear combination of them. And proceed in this way so that at the kth step you write WK as R1K U1 plus dot 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 RKK UK. And this is kind of a what's called a triangular system. If you write these numbers down in a matrix, it looks like this. With zeros up here. And this is, when I'm done, if I can do this, I will have an orthonormal basis U1 through UN. And all I need to do is figure out what the Rij's are. And, well, I'm not going to work this out in detail. It just takes a couple of steps. But see page 232 in the book. It turns out that Rij has a rather nice formula. It's simply Wj paired with Ui. And let's see, this is for all I running from 1 up to j minus 1. And let's see, is this a reasonable formula? So to compute Rij, I need to know Wj, that's fine. And then I need to know all of the UIs, all the preceding UIs, and that's what I've computed. And so you can compute the next Rij by this formula. And then this gives you the formula for Uj is Wj minus R1j U1 minus dot 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 minus Rj minus 1 Uj minus 1. Sorry, I'm running out of space, but I want to squeeze this in here. That's a vector which is orthogonal to all of the previous ones, and then you have to divide by its norm, which is this Rjj. And so this gives a procedure where you compute the UIs directly, and it's kind of nice because you don't really have computationally it's somewhat easier. All you're doing is you're taking the inner products at each step of a vector with another unit vector, and you do have to do this one step where you normalize here, and it's not too bad. And I should say the last thing is that this Rjj has the formula. Well, I'll write down Rjj squared is the length of Wj squared minus R1j squared minus dot 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 Rj minus 1j squared. Okay, so I'll also do an example of this in class, but this is a variant of the Gram-Schmidt procedure where you get the UIs at each step rather than waiting till the end.